Now that we've seen Green's theorem, let's do some reformations of Green's theorem, knowing our three-dimensional vectors and our curl and divergence that we've already learned. So we include our typical 2D thought into R3 as the xy plane. So this means tacking on a 0 in the k component. So f of xy is now p of xy, q of xy, comma 0. So in other words, r is just equal to 0 when we were thinking of curl and divergence. So the curl, therefore, if you do this, is just going to be 0, 0, qy minus px. So Green's theorem would read that our closed line integral of the boundary of D of f dot dr is just going to be the double integral of D of the curl of f dot k with dA. Pretty easy way to think of that. If you want to do some work to make sure you know this is true, but it's just a reformation of Green's theorem. Add what we know here, what we know about curl, Green's theorem, bada bing, bada boom. So let's think of a different way. If you remember, the closed line integral of the boundary of D of f dot dr is equal to the closed line integral of the boundary of D of r dot the tangential component ds. So again, this is integrating the tangential component of f. Now let's recall what is the normal component. The unit outward normal of n, the vector n, will just be 1 divided to the magnitude of r prime of t times, this is, remember, a scalar function, of y prime of t, comma, negative x prime of t, 0. Now f is still our same p, q, 0. And r is bounded in this sort of fashion, which is why the n component makes sense in this regard. So let's do another reformation of Green's theorem. So we have our f dot n ds, right? Which we know is a to b of f dot n of the magnitude of r prime of t dt. Okay? Now, using our substitution that we found, we have our p of r of t, comma, q of r of t, dot our y prime of t minus x prime of t dt. Now remember, this is coming from over here, our dot dr. And this is our dr when we have things in terms of t, parameterized that way. We do our dot product, which you should be very familiar with now. And when we simplify this, we are just going to get our p dy minus q dx over the closed curve that we can formulate with r, which we can just use Green's theorem to say this is the double integral over d of px minus qy dA. But what is px plus qy? Because we don't have a k component, it's just going to be the divergence of our original f. So another reformation of this theorem is if we have this f dot n ds, it's just going to be the double integral of the divergence of f dA. So hopefully these reformations of Green's theorems give us some more mathematical tools with using curl and divergence. This kind of method should work for your other types of integrals. So I would maybe create a interesting situation, maybe two holes or something like that, or odd situation, and see if you can kind of piece together to get used to orientation and how to add and subtract these integrals in terms of their boundaries.